Let's take a look at an example from section 9.4 dealing with inferences for two dependent means. Here we have data from 6 plants where they have calculated mean man-hours lost per month over a 1-year period, both before OSHA was implemented and after OSHA was implemented. We want to test the hypothesis that OSHA has been effective in reducing industrial accidents. This is dependent data because it is a before and after effect. So we have to use different techniques than we do for dependent means. We're going to perform a test to see if OSHA has been effective in reducing industrial accidents, and we'll calculate our differences as before minus after. And we'll put these in the table, although I'm going to use Excel. So I have my data here already plugged into Excel, and I want to calculate the difference of before minus after. So we'll do equals before minus the after, and 38 minus 31 is 7. Now you're probably thinking, there are only 6 points, I can do this in my head, I can write them down. That's okay, but we've got technology and we're going to have to use it anyways to calculate the mean and the standard deviation, so let's take advantage of it. I'm going to drag that formula across, so I click on the mouse, I hold the button down, and I drag my mouse across. And that automatically populates the other cells. So I have my differences. Part B asks for the average reduction in man-hours lost per month in the sample. So I can find my average by selecting that row of differences, and I get 4. Just like before with averages, if I add up these numbers and I divide by how many I have, 7 plus 6 minus 1 plus 5 plus 6 plus 1 will give me 24. Divided by 6 is 4. To calculate the standard deviation, we'll use standard deviation.s for a sample. And I'll select that same data as before. And we get 3.224903. So we're able to find our mean and our standard deviation, and now we can go back and form our hypotheses. So going back to our problem, we have our hypotheses. The mean difference is 0 will be our null hypothesis. And then for our alternative, since we want the average difference, this is where the wording of the problem can get confusing. Since we have before minus after, we want to show that OSHA has been effective in reducing the accidents. That means that our before values need to be greater than our after values, or before minus after needs to be greater than 0. So we could look at it this way: before is greater than after. Subtract after from both sides, we get before minus after is greater than 0. Before minus after is our average difference, so we want that mu sub d to be greater than 0. And this will be our claim. From these hypotheses, I get that this is a right tail test. Well, now I need to calculate my critical value and my test statistic. Calculating our critical value, because I have a right tail test, I'm going to do 1 minus alpha. And alpha for this problem was 0.05, so we'll do 1 minus 0.05. Our degrees of freedom is n minus 1. 6 minus 1 will give me 5. And so I can calculate that. Critical value is 2.015. To get my test statistic, my formula here, d bar minus mu sub d divided by s sub d divided by square root n. Or, since mu sub d is 0, d bar divided by square root of s over n. And I'm going to make Excel calculate this one. since I already have my mean and my standard deviation here. So we'll do mean divided by, parentheses, standard deviation over square root n is 6. Yes, give me another parentheses. And we get 3.038, which is 3.04. We could calculate that by hand, but since I already had the values in there, I just decided to use Excel. Giving us a little bit more room, let's set up our graph. Critical value 2.02 and the rejection region. And then our value, test statistic 3.04. It's far in the tails. We would reject the null, which means there is enough evidence to support the claim that OSHA has been effective at reducing lost man hours.